Okay, good afternoon, good morning, good evening, good night, depending on when you're watching this video. In this video, we are going to work through the exercise on slide 25 of lecture set number 10. So this exercise is going to demonstrate a chi-square independence test. Chi-square independence tests are used when you have two qualitative variables, and each qualitative variable has two or more outcomes associated with them. And we are interested in determining if one, or rather, we're interested in determining if those qualitative variables are associated with each other or not independent of one another. So for example, in the slide shown, or in the example shown on slide 25, we have a study that is used to determine the effect of vitamin C on the common cold. An experiment consists of an experiment utilizes 279 people, so that's our sample size. And the results of this experiment, which is essentially counting how many people have the cold, how many people suffered from the common cold or did not suffer from the common cold, given they were administered a placebo or vitamin C, are listed in the contingency table. So for example, we have 31 people that were given a placebo and had a cold. And then we had 109 people that were given a placebo, so maybe like water tablet or something like this, and they didn't have a cold. And then we have similar counts for ascorbic acid. Okay, so these 17 people said they have a cold and they're given vitamin C, or they took vitamin C and got a cold. And then 122 people took vitamin C and then didn't have a cold. Right? And the question says, at the 5% level, do the data provide sufficient evidence that the effect of ascorbic acid and the common cold are related? Okay, so there's a lot of different ways to phrase this type of problem, but in general, if we're asked for an association or if we're asked if these two variables are independent or not independent, this would be a chi-square independence test. Data for independence tests always present themselves in two-way tables. So that's sort of a giveaway that this is the kind of test you should be considering. And the steps of the test are exactly the same as the steps of a chi-square goodness of fit test. The only difference between a goodness of fit test and a independence test is how the expected values are computed. So that would be that preliminary step. And how the degree of freedom is computed on step 4 of the hypothesis test. All right, so for example, for this test, the first thing we need to do are work out the expected values that are associated with each outcome in the contingency table. Okay, so I'll call this a preliminary step. All right, so what I need to do here is compute an expected value for each of the 4 outcomes in this contingency table. So for example, the expected value for cold and placebo. Okay, so this is how many people I would expect to say they have a cold, given that they are not, or they're taking some water tablet, across the 279 people, if it is true that these two variables are independent of one another. Okay, so to compute expected values in a two-way test, we take the row total, we multiply by the column total, and then we divide by little n. So we're going to have R times C over little n. Okay, so our row total is 48 multiplied by our column total, which is 140, divided by our sample size, which is 279. And this gives us 24.08602. So basically what we're saying here is if having the common cold or not having a common cold and taking ascorbic acid are independent, so if they are not related, we would expect about 24 of the 279 people to say that they have a common cold if they took a placebo. Right, now we need to repeat this exact same process for the the 3 remaining values or combinations in the table. And the process is exactly the same. All that's going to happen is we're going to shift the row and the column we're working in. Okay, so for example, the expected value or the expected number of people that say that they have a cold but we're taking ascorbic acid or vitamin C is going to be the row total, which is 48, multiplied by the column total, which is now 139. Okay, so notice that I have moved for this count. These are my row and column totals now. Okay, so you can see how we're just sort of shifting our way or moving our way through the table. And each time we change a cell, our row or our column total is going to change. Okay, so this gives us 23.91398. Okay. All right, so now I need to get the expected value of not having a cold and taking a placebo. So now my roll total is 231 multiplied by my column total, which is 140, divided by my sample size again, which is 115.91398. And then finally, I need the expected value or the expected number of people that do not have a cold given they are taking ascorbic acid. And this is going to be 231 multiplied by 139 over 279, which is equal to 115.08602. So these are my 4 expected values. And now that I have these quantities, I can move into the assumption checking step. So the assumptions of a independence test are exactly the same as the assumptions of a chi-square goodness of fit test, right? So the first assumption is that no expected value is less than 1. And this is true because you can see that our lowest expected value is 23.91398. 23.91398 is bigger than 1. So therefore, no expected values are less than 1. Our second assumption is that no more than 20% of expected values are less than 5. Okay, well, again, this is fine because we don't have a single expected value less than 5. Every single expected value that we computed is bigger than 5. So 0% of the 4 expected values are less than 5. And then the last assumption is our classic SRS assumption. There isn't any information in the question that says directly that we have collected a random sample, but so we can't really check this off. This is unknown. So we'll have to make a note of this in our conclusion. All right, so now we can start the hypothesis test. Okay, so on step 1, our null hypothesis is that the common cold and the effect of ascorbic acid are independent so that they're not related. Okay, so we can write, for example, the common cold and effect of ascorbic acid are independent versus HA. And then we'll have here basically the exact same sentence, except we would say are not independent or are associated with each other. And there's a lot of different ways that you can phrase it. So I'm going to write it as are associated. Okay, so the null hypothesis in an independence test is always that the 2 variables are independent of one another. So it would just be, in the standard case, variable 1 and variable 2 are independent. The alternative hypothesis is the opposite, so that they basically variable 1 and variable 2 are not independent, or are associated, or are dependent. This would mean the same thing. Okay. So I've used the terminology independent versus associated, but you could say independent versus not independent. Right? So this is the purpose of the test. Now in step 2, we state our significance level, which is 0.05. On step 3, we compute our test statistic. So this is the exact same test statistic that we used in the goodness of fit test. So we have observed minus expected squared over expected. So the sum across those values. Okay, so for example, our first calculation will be 31 minus 24.08602. Okay, so this is going to be 31 24.08602 squared divided by 24.08602. Okay, and then we're going to take our second expected value. It doesn't matter what order you do them in as long as you do all the pairs correctly. So our second one, we'll just move across the table, is going to be 17 minus 23.91398 squared divided by 23.91398. And then our third expected value will be 109. I'm going to move this down. Okay, so now we're going to go 109 minus 115.91398 squared over 115.91398 plus, and then our last one will be 122 minus 115.08602 squared over 115.08602. All right, and then if we work all of those quantities out, we should end up with a test statistic of 4.811. Okay, so our test statistic here is 4.811. Okay, so now on the fourth step, we can take either the critical value approach or the p-value approach, right? You don't have to do both. As always, they're going to agree, but I will demonstrate both just so that we have illustrations of both. Okay, so we're running chi-square test now. So this means that we are testing using a chi-square curve. So we're going to sketch out a right skewed curve. Something looks like this, for example. All right, and then our first, if we're using the critical value approach, what we are looking for is a critical value on some degree of freedom and 0.05. Okay, so the degree of freedom for a independence test is the number of rows minus 1 multiplied by the number of columns minus 1. So this is going to be 2 minus 1 times 2 minus 1. Because if we go back to our contingency table, you can see we have 2 rows, cold, no cold. That's the number of rows, so 2, and 2 columns, placebo and ascorbic acid. So the number of columns is 2. Okay, so we're going to have 2 minus 1 times 2 minus 1, which is simply 1. So we have a critical value on 1 degree of freedom and 0.05. So we go to our chi-square table. We match our degree of freedom, which is 1, to 0.05, and that gives us a critical value of 3.841. So we come back here, we have 3.841. Our test statistic is 4.811. Right, so we can see that our test statistic is inside the rejection region, so we are going to reject. Now, if we take the p-value approach, this will work in the same way that it did before as well. So we sketch out our chi-square curve. We mark down where the test statistic is located in this case, and then we shade the area above the test statistic. So our p-value for this test is the probability that a chi-square random variable exceeds 4.811. Okay, so we go back to our chi-square table. Notice again that the chi-square table works exactly like a t-table works. Okay, so we scroll across the line and we're looking for 4.811. You can see that 4.811 sits in between 3.841 and 5.024. So our p-value is going to be between 0.05 and 0.025. Okay, so we come back here and we can say since 0.025 is less than the probability of interest is less than 0.05, then 0.025 is less than the p-value is less than 0.05. Okay, so now we can see if we were on step 5 of the approach, regardless of which approach we take, our conclusion is the same. So reject H0 since test statistic is in rejection region. Or if we take the p-value approach, we would say reject H0 since the p-value is less than alpha. Okay, and then the last thing we have to do as per any hypothesis test is conclude. Our concluding statements are going to work in the same way that they've done for the other tests, except we are just phrasing this in terms of the alternative for this particular test. So we would say at the 5% significance level, the data provide sufficient evidence to suggest that the common cold and effect of ascorbic acid are associated. So essentially what we've been able to do here is determine that taking ascorbic acid and the presence of the common cold, they are related to one another. So those are not independent variables. Okay, so that's an illustration of a chi-square goodness of fit or independence test. It works in the same way as the chi-square goodness of fit test. The only difference are the null and alternative hypothesis and the computation of the degree of freedom. So the applications of the two tests are fairly easy to distinguish. We use a goodness of fit test when we are dealing with a qualitative variable that has 3 or more outcomes. And we use an independence test when we are trying to determine if 2 qualitative variables with 2 or more outcomes each are associated with one another. Okay, so as always, if you have any questions, please let me know.